video tutorial that's going to look at integration, the fundamentals of integration, so more of a beginner's guide. So there's not going to be many complex examples in this video. It's more just going to lay out the different notations and the formulas. So before I go into the general form of integration that I've written up at the top right, to make more sense of that, we're just going to go through some sentences that will clear up and make more intuitive sense as to what's going on, and then applying that knowledge to the general form, hopefully the connection will be made a lot more easily. So the first one is integration is the reverse of differentiation. So it might sound a bit counterintuitive as to, well, differentiation is just like a mathematical operation, so how can you get the reverse of something like that, which is very valid. And when I started calculus, I had the same questions, but after a while I kind of denoted these two nearly like a direction to integration and differentiation. So what I mean was, if I was given a function f of x and I was asked to differentiate it, I would nearly look as if we were going in the downward direction to give, and the result of that would be the differentiated function. So then conversely, when we are now going to integrate, it's like we're going up above the function, let's say, and that's going to be the function integrated. So another name given to this fact would be the antiderivative. So suppose I gave you a function f of x is equal to, I don't know, 3x squared. And if I told you that this was a differentiated function, so let's say, it might make it easier, just have f prime of x. Right, so I said to you, this f prime of x is 3x squared. So then I've given you the differentiated result, 3x squared. So then if I said to you, okay, this is the differentiated result, but what is f of x? So I've given you f prime of x, so then what is f of x? So what you would probably tell me is that the initial function f of x is equal to x to the power of 3. So why would you say that? Well, if you differentiate f of x, so the one we have here, so if we differentiate x to the 3, what do we get? Well, we bring down the power and we reduce the power by 1, 3x squared. Can you see here that they're the same? So you managed to work out the original function f of x from looking at its derivative. So then what we're seeing here is that this x cubed that you figured out, that is the antiderivative of our original function. So you were given the differentiated result, and then you were asked for the original function, f of x, which we found to be x cubed. So this is the antiderivative function. All right, so this is the general idea behind what integration is fundamentally. So if you can understand that concept, what we just went through there, we can then take that knowledge and we can go up here and look at the general form for integration. So we've kind of already explored it without realizing, and all this fancy notation implicitly it represents what we had done here already. So we'll just go through it component by component. So this first sign here it's like an elongated S. So it's the symbol for integration. To the right here then we have an f prime of x, or just a function. It could just be f of x, just a function, and that's called the integrand. So the function that we're going to integrate is called the integrand. And then at the end we have what's just called a variable of integration, which is basically just attached at the end. It doesn't actually come into when we're physically integrating the function. And now that integration is equal to f of x, which is just going to be the integrated version of f prime of x. If you can see, we did that here. So we had our f prime of x here. And then when we integrate it, we get an f of x, see down here, which we did here. But then there's this little thing at the end, a plus c, which we didn't have here. And that's called the constant of integration. So that's what we're going to look into now, is to what is this constant of integration. All right, so the constant of integration, just the example I'm going to give, just as an aside, I'm going to write over here, just like differentiation where we have the power rule, you know, where you bring down, when you have an x to the n, you're going to bring down the power, you reduce it by 1. So if you remember, that's the power rule in differentiation. We also have a power rule in integration. So it's very similar in that if we want to integrate this function with a power, so instead of differentiate, so if we want to integrate a function with a power, that's then going to equal the function, which is x, and unlike differentiation, we're actually just going to increase the power by 1, and then we're going to divide the whole thing by that power. All right, so pretty straightforward. So if we want to integrate a function with a power, the result of that integration is just the function, and the power is raised by 1, and it's all divided by that raised power. And then you have your constant. Okay, so we have this a little aside here. All right, so then if I gave you another function that was just 5, so we know if we differentiated this, it would go to 0. Now I want to find the antiderivative of this function. So just like before, I gave you a function here, I'm giving you a function here as well. So what I'm doing here is this example is going to explain why we need this constant at the end of the general form. Right, well, when we integrate this, so this is essentially going to be using the power rule implicitly, because it's like we have an x to the 0 there. So when we integrate it, we're going to raise the power of this x to the 0. So it's going to be, so the integral of this f prime of x is going to equal 5x plus c. Now, just going back to this, we have the differentiated version, so we know if we were to differentiate 5x, we would get 5. So we know that it's the antiderivative, because if we differentiated 5x, we would get 5. But what if I said to you that, okay, the antiderivative might be 5x, but what if I said, what's the differentiated result of 5x plus 4? So if you were to differentiate that, what would you get? Well, you would also get 5. So you have a 5 here, but also here. So what you're saying then is that, okay, well, am I saying that 5x is equal to 5x plus 4? Well, that can't be right, because this has a 4 and this doesn't. There seems to be some sort of breakdown here. Well, the breakdown is that we don't have a set value for what this might be when we integrate. So instead of coming across this kind of conflict, we just put in a plus c, which is just a constant, which essentially means that, yep, this result can have any constant attached to the end. We don't exactly know, but to make the operations work, we'll just have a plus c at the end, which kind of encapsulates all what might have been attached to that antiderivative. The rules that I'm about to write out and show are kind of the first few that you would encounter when you're doing integration assignments or just general revision. So I'm just going to write, I think there's 3 fundamental rules, and I'll attach one example to each to kind of clarify the point. We know that we differentiate a constant that equals 0. So again, I'm just going to do a quick example for each. So if we were to differentiate, I don't know, 7, we know that's equal to 0. Okay, then the integrated, if we want to, well, this is kind of done for us. If we want to integrate 0, which we get here, that's going to give us that constant, or not exactly that constant, because as we discussed previously, it could be any constant, hence why the result is C. So this next one is the differentiated version of this rule. It's quite straightforward. You've seen it many times before. When you differentiate a coefficient, any coefficient with a function x, this turns to 1 because x to the 1 when the power goes to 0 is just 1. So we just get our constant back. And then the equivalent rule is when we integrate, so see what's going on here. So we differentiate a function, we get k, but then if we were to integrate that function, we go back to the original function, and that's why we get our k of x here, and then the plus c as we discussed before. So these are the two kind of, if you remember, the directional cues that I had. So we differentiated, we went down to get a k, but then when we integrate this k, we're going back up to this original k of x function here. And an example of this would be, I'll go different color. An example of this would be, we have d dx of 10x. So we know that's equal to 10. So then if I was to say, okay, k is 10, so integral of 10 dx, well, again, from the power rule before, we know that we get an x is going to be here, we're going to raise it to the power 1 and divide by 1, which in essence, or not in essence, exactly just gives us 10x, again, plus our c. We can't forget this constant, because then if we don't have that constant, as we said, we could have an infinite amount of antiderivatives, because this could be 10x plus 1, 2, 3, 10x plus pi, so on and so forth. So we can't forget the plus c. So once again, we differentiate to get value, then we integrate it, and we get back that original function. So this is the second rule. So the final rule I'm then going to go through is one that we're familiar with in differentiation, where if you have two individual functions, so in this case f of x, and then you have a plus or minus a second function g of x, when we want to differentiate these expressions, we know we apply it individually. So we just differentiate our f of x to get f prime of x, and then we integrate our g of x separately to get g prime of x. Well, it's the same situation in integration. So if you want to integrate a function, so two functions that are separated by like a summation or a minus sign, you're then just going to integrate each function individually. So then what you do to integrate these expressions is you first integrate the first function, and then you can integrate the second function. So an example would be if I want to differentiate, okay, so we have x squared and we have plus or minus 5x. So when we differentiate this, we know that the x squared goes to 2x, and then this 5x will just go to 5. So we see that we just differentiated each expression individually to get our final result. And similarly here, if we want to integrate this f of x, which we chose to be x squared, and then plus, what do we have, 5x d of x. So that's equal to, well, we say we integrate the first function here. So remember, we raise the power by 1 and divide by it. So then this is going to change to x to the 3, because we raise the power, and we divide by 3. And that is, what, explicitly you can have the plus c here, and then you have the plus or minus the second function integrated. So this 5x is going to change to 5x squared over 2, because we're dividing by the new power, and we have our constant of integration. So yeah, they're the three rules that you'll encounter when starting off integration. So I hope they made sense. There's obviously from here, which I'll do in the next video, you'll be integrating with exponentials, trigonometric functions, integration with two functions in product with one another, which requires a whole different setup. So I hope you enjoyed the video. I hope you found it useful, and it was clear enough to follow. And if so, if you don't mind giving the page a subscription and a like, and even the notification bell, so you know when the next tutorial video is going up, would be much appreciated. So thanks, and see you in the next video.